Hi, Aidan Luntry here again. Welcome back. This is Higher Level Maths for Leaving Cert, 6th year. And this is Course B, which is Paper 2. And this is Day 4 and Ordinary Paste. And the topic for today is probability. Now, again, you will have got a number of notes on probability. But the only one that you need to have handy while we're doing this particular class here is the question sheet, which says probability, ordinary paste, and then questions. Now, the questions that we're going to be tackling will, for the most part, come from this particular sheet here today. So, let's get going. Now, so for probability, the first thing that I have to mention is, because we're going to need it later on, we're going to have a brief review of what are called counting techniques. This involves being able to count the number of possible outcomes when an experiment is performed. And it's an idea that's used frequently and all over the place really in probability questions. Now, the first idea that we have here are the so-called fundamental principles. And there are two of these. First up, many times when we perform an experiment, we realize that the experiment consists of stages, and we don't have any outcome at all until all stages are complete. For example, if an experiment consists of 2 stages, we don't get an outcome until we finish stage 1 and stage 2. Now, in this sense here, to count the number of outcomes when there are 2 stages like that, we count the number of ways of completing stage 1, we count the number of ways of completing stage 2, and then in the context of counting outcomes for an experiment, the word "and" means that we multiply. So "and" means multiply, and that refers to a situation where an experiment occurs in stages. The second fundamental principle applies to a situation where, when we read a question, we realize that the outcome that they're talking about can occur in one way or in a completely separate way. So there are options for how the experiment may be performed. Now, in that case, what we do is we find out the number of ways of completing the experiment by the first method, and we find out the number of ways of completing it by the second method. And then, in the context of counting outcomes, the word "or" means that we add. So this refers to when there are options. Now, that's the first fundamental principle. I'm not going to give you any examples of that right now. It's going to occur frequently enough in what we do later on, so you'll see it often enough to get the idea of it. Now, the second of the counting techniques refers to the idea of arrangements, also known as permutations. Now, the key thing about arrangements or permutations is that we're talking about placing objects in order. So in other words, order is important. Now, we have 2 little formulae in here. The first of these is when we want to arrange all of n different objects. The formula for doing that is n factorial. So to arrange all of 4 different objects in a row, then the number of ways of doing that would be 4 factorial. I'm sure you remember that 4 factorial, for example, is 4 by 3 by 2 by 1, which is 24. But we can work it out on a calculator as well. Right, now, the second thing is, here for arrangements, we may not be asked to arrange all. We might be asked to arrange some. I'm going to be specific here about this. I'm going to say some, or from n different objects. And there is a notation for this. It is NP, P for permutation, and then OR. So the upper number is the number of objects that we have in total. The lower number down there is the number that we are arranging. Now there is a formula for this, but it's not really important. What's important is that you're able to use that particular function on your calculator. So on your calculator, there will be a button, and over that button, there will be the function NP/OR. So you just need to be able to use that. We'll be seeing these as we move through the rest of the class here. Now, the third and the last of the counting techniques, just briefly to refer to here, is the idea of combinations. Now, other names for combinations are choices or selections. And the big difference between these guys, the combinations and the arrangements, is that order does not matter. So order is not important. So when we choose a number of objects, there is no idea of a first, a second, and so on like that. Now, so there's only one formula here that matters, and that is choose or from n different objects. And the number of ways that can be done can be written down like this. Big pair of brackets like that with n over or. The total number of objects that we're choosing from goes on top, and the number of objects that we're choosing goes down below. Now there is another notation for that. It looks like this. This is the more, if you like, old-fashioned notation there. This is the one that's currently in use. This is the one that's in the maths tables, and if it were to be asked directly in the exam, this is the one that would appear in the exam paper. Now, again, there is a formula for NCOR, NCHOOSE-OR as many people call it, but the important thing is that you're able to use your calculator to work out this. And again, you're looking for a button on your calculator that has NCOR written over it. And we'll see it now in a couple of minutes. So these are some of the counting techniques that we're going to be using as we go through the questions on probability. These guys can be examined in their own right, but we're going to examine them here in the context of doing probability questions. Very good. Just mentioning that now. I'll leave it over here for a minute. So now we move on to probability itself. Now, there are a few key concepts that we look at in probability. First of all, there is the idea of the experiment. Now, in a probability question, the experiment is the activity that is being undertaken. In other words, basically, what is going on? What are you doing? And when you try and identify the experiment, this is without any reference to any kind of outcome that you may or may not want to happen. Now, it is important that for the experiment, you understand the idea of the sample space. The letter that we have for the sample space is S. And the sample space consists of the set of all possible outcomes. I'll give you an example. Suppose that we throw a die, an ordinary six-sided die. Well, the sample space then consists of the whole numbers 1, 2, 3, 4, 5, and 6. They are the numbers that we could possibly get when we perform that experiment. The next thing that we talk about after the experiment and the sample space is the idea of an event. Now, there are different letters that we can use to represent an event. The most common one being E, but you will see other ones like F and A and B being used. The event is what we want to happen, what some people describe as the set of favourable outcomes. So, for example, again, referring back to the idea of throwing a die, where the experiment is that we throw the die and the sample space is that we get one of the numbers 1, 2, 3, 4, 5, 6. If the event is that we want to get an even number, then the event can be written down as the set of numbers 1, 3, and 5. Now, because there is this very strong link between probability and set theory, if we want to represent these on a Venn diagram, the usual practice is to represent the sample space as a universal set. And as you know from junior cert, that means being represented as a rectangle. So there's your sample space, and then your event will be a subset of the sample space like that. So that's what we're talking about in any probability question. Now, the next thing that we talk about is the idea of the probability of E. Now, the probability of an event E is written down as capital P in brackets and then with E in brackets after it like that. So the probability of E is written down like that. Now, what do we know about the probability of E? I'm not going to give you a straightforward definition of the probability of E just yet. I'm just going to say that in any question, the probability of an event E must be a number between 0 and 1. So therefore, if you feel like writing down that the probability of some event is 2, please don't, because it can't be 2. It can't be bigger than 1. Now, those two numbers there, 0 and 1, they're the two extreme cases. And what do they correspond to? Well, the probability of 0 corresponds to a situation which can't happen. Impossible. So if the probability of something is 0, well then it can't happen. At the other extreme, if the probability is 1, well then the event must happen. Now, in most practical questions, the probability will end up being some number in between the two of those. The next thing that we have is that the probability of the sample space is 1. In other words, by the very definition of the sample space, when the experiment is performed, what happens must lie in the sample space. Okay, so whatever the outcome is, it must be in that, if you like, universal set there. Now the next thing is an attempt at a kind of a definition of the probability of the event E. The probability of the event E is the long run relative frequency of E. Now, that's all very well theoretically, but it's not very practical. I'll explain it now. Long run relative frequency of E. So, for example, if I had a coin and I wanted to find the probability of getting a head when I toss that coin, what I could do is conduct an experiment. I could toss that coin, let's say 100 times. And let's say that I found that when I did that, a head turned up 54 times. Well then, based on my experimental evidence, the relative frequency of getting a head would be 54 over 100. Now, somebody might complain that, look, to find out the true probability of getting a head, tossing the coin 100 times is not enough. And they would have a point. So maybe I would start over and I would toss the coin this time round 1,000 times. And let's say this time round the head turns up 507 times. Well then, the relative frequency now, giving me the probability of getting a head, would be 507 over 1,000. And again though, somebody could complain and say, that's not enough. You need to toss it more often than that. So we could toss the coin 1,000,000, 1,000,000,000, and so on times. And as we toss it more and more times, the fraction, the relative frequency fraction, should, if the coin is fair, get closer and closer to a half. And that's why we would say that if you were to toss a fair coin, the probability of getting a head is a half. And that's the idea of the definition of the probability of E. The problem is that it's not very practical. So we've got different methods for working out the probability under certain circumstances. So let's start off now with the probability for equally likely outcomes. Now, I'm just going to say here to begin with, suppose that each outcome in the sample space in S is equally likely. In other words, has an equal chance of occurring. And I'm going to say here, let the cardinal number, now that hashtag symbol there, okay, in the context of sets, means the cardinal number of a set, means the number of elements in the set. So let the cardinal number of S be n. And let then the cardinal number, the number of elements in E, the event E, be R. And then in that case, we have a really very, very convenient formula for working out the probability of E. We can say then the probability of E is equal to R over N. Now, in easy questions, working out N and then R is relatively simple. But as the questions get harder, we find that in order to be able to work out N and then R, we quite often have to use the counting techniques that I listed at the beginning of the class here. So right now we're going to go to the question sheet. We're going to have a look at question 1 on the question sheet. We'll just read it here first of all. So question 1 on the question sheet says, there are 16 discs in a board game. 5 blue, 3 green, 6 red, and 2 yellow. Okay, 4 discs are chosen at random. And then we're asked for different things. What is the probability that? And we get different things here. So I'm just going to say, okay, what have we got here? We've got 5 blue. I'm just going to use B for blue. We've got 3 green. And I'm going to use G for green. We've got 6 red. And I'm going to use R for red. And we've got 2 yellow. And I'm going to use Y for yellow. So that's the discs that are involved in this board game. Now, according to the question here, 4 of these discs are chosen at random. That's the experiment. In other words, all of those discs, 16 of them, are put into a hat. Somebody puts their hand in without looking and picks out 4. Now, they're chosen, which means that there is no order. So the experiment here, and writing the experiment down using what's called probability language, we're going to say we are going to choose. Okay, so we always start with the verb. The verb will be either choose or arrange. And in this case here, it's choose and then followed by a number. So we're going to choose 4. And then the word from. And how many are we choosing from? And the answer is the whole lot. And they've told us that the total number of discs is 16. So therefore, the value of n will be 16 choose 4. Why? Well, in theory, each combination of 4 discs has an equal chance of occurring. It's equally likely. So it's going to be 16 choose 4. Now, on the calculator, let's just pop it over here so people can see it. Yep, so it's going to be 16 on the Casio here, 16, and then I go shift, and then divide, and that gives me the C, and then 4, and then that's going to be equal to. So the answer for that is 1820. Okay, so that's the overall number of ways of carrying out the experiment. That's the value of n. Now, in the first part of the question here, the event, we'll call it E, the event E is that all 4 discs are blue. So I'm going to say 4 blue discs. Now, I think we all understand the idea. It's not particularly likely, but if somebody puts their hand in and picks out 4 discs at random from that bag with the 16 discs, and then they look at them, what's the probability that all 4 of them are blue? Fine, well, we're going to calculate that now. But again, we need to write that in probability language, and that would be to choose 4 from all the blue discs that there are, and that's 5. There are 5 blue. So the OR value for that would be 5 choose 4. And we just work that out. 5 choose 4, and that's going to be 5. And therefore, the probability of that event is going to be OR over n, and that's going to be 5 over 1820. And we can let the calculator simplify that fraction for us. 5 over 1820, and that's 1 over 364. Okay, so that's the answer for the first part of that question there. Now, the second part of that question, it's a different event. It says, 2 of the discs are blue and 2 are not blue. Fair enough. Okay, I think we understand the idea. We put our hand in, we pick out 4 discs, and when we open our hand to look at them, 2 of them are blue and the other 2 are of other colours. So we can say 2 blue and 2 not blue. Okay, now again, we need to write that down in probability language. Now, because we have the word and here, there are going to be different stages. So we can say here, we can choose 2 from 5 blue to begin with, but that's only the first stage. There is the second stage. So the link word here is the word and. So as well as choosing 2 from the 5 blue, we need to choose the other 2 from, I'm just going to say the others. Now, out of a total of 16 discs, if 5 are blue, then 16 minus 5, 11 are not blue. So I'm just going to say choose 2 from 11 others. Okay, so from that then we can say OR is equal to 5 choose 2. Now, from the fundamental principles that we had at the beginning of class, what does the word and mean we do? And means that we multiply. And then that will be multiplied by 11 choose 2. Grand, so, and we can just work that out on the calculator. So I'm just going to go 5 choose 2, and then multiplied by 11 choose 2 as well. And then the calculator will give me the answer for that, and that's going to be 550. So therefore, the probability of that event there is just going to be OR over n again, and that is 550 divided by the n value that we had up there, 1820. And if we check that out on a calculator, that's going to be 550 over 1820. And okay, looking at that, the only thing that divides above and below is 10. So we get 55 over 182 for that. Very good. Okay, so that's the end of that particular question there. Now, that formula for working out probability, the OR over n formula, it does require that each of the individual outcomes in the sample space is equally likely. That condition, unfortunately, is not always met. And I'll give you an example. Suppose that we have a pair of dice, 2 dice, and we throw the 2 dice, and when the 2 dice stop rolling, what we do is that we add up the numbers. So for example, if I roll a pair of dice, and one of them shows 5, and the other one shows 3, then what I do is I record a total of 8. Now, let the sample space then be the set of all possible totals that you could get. What's the smallest element in S? The smallest element in S will then be 2. You cannot get a total less than 2 when you throw 2 dice. And the largest element in S will be 12. You cannot get a total larger than 12. So for that reason, the entire sample space will be all the whole numbers from 2 up to 12 inclusive. But are they all equally likely? And the answer is no. How many ways are there of getting a total of 2? The answer is there's only one way. You must get a 1 and a 1 when you throw the 2 dice. On the other hand, how many ways are there of getting a total of 7? And the answer is loads. There are loads and loads of ways of getting a total of 7. You can get a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, a 6 and a 1. For that reason, you are far, far more likely to get a total of 7 than you are to get a total of 2 if you throw 2 dice. And there's an example of where the individual outcomes in a sample space are not equally likely. So now we need to extend the idea of probability to take into account situations like that. And that leads us to what we have here as what's known as general probability. Now, what general probability does, first of all, it doesn't run against this formula here. Whenever this formula does apply, we can still use it. We're not going to deny that formula. It's very good in the situations to which it applies, but we need to move on from there. So, to extend the idea of probability, we, if you like, strengthen the link between probability and sets. So, from junior cert, you may remember some of the ideas that you had about sets. Well, we're going to tie those in with probability now. So if I have a look at some concepts from sets, and we have a look at those in the context of probability as well, let's see what we can say. First of all, let's suppose that we have 2 sets or 2 events, A and B. Now, on this Venn diagram on the side here, back at junior set level, what name would you have given to that region there? Well, you would have called that region there A union B, which is grand. Now, what do we call, though, that region there in probability? Well, the name for the region in probability refers to the condition that must be met for an outcome, or if you like, an element, to belong to that region there. And for an element to belong to this region here, it must belong to A or to B. So in terms of probability, we call that A or B. And from now on then, in the entire area of probability, the symbol union and the word or are completely interchangeable. Any formula that has one or the other can be, without a shadow of a doubt, just replaced by the other one. Now, the next one that we have a look at here is if we take 2 sets or 2 events, and what name would we give to that region there? Well, that region there, as I'm sure you remember from junior cert, that's called A intersection B. But what do we call that region there in terms of probability? Well, again, the name for the region refers to the condition that must be met for an outcome to belong to that region. And for an outcome to belong to this region here, it must belong to A and to B. So we call that A and B. And again then, going forward, the symbol intersection and the word and are completely interchangeable here. Now, the next diagram we're going to have a look at refers to 2 sets or 2 events, A and B, which don't overlap. So we can say here, A intersection B is the null set. Now, there is a name for that scenario in set theory. It's not so commonly used these days, but I'll give it to you anyway. We would say in sets there that A and B are disjoint. So they are disjoint sets. You don't hear that being used very much nowadays. But the name for this, in terms of probability, is highly important. And this is the idea that A and B are called mutually exclusive. It's one of the most important phrases that we have in probability questions. mutually exclusive. Now, it is important that you understand that particular terminology there. Two events are mutually exclusive. Let's focus on the word exclusive first of all. The word exclusive comes from the word exclude. So A and B are mutually exclusive if, first of all, if we know that, for example, A has occurred, that excludes B from occurring. And mutually means both ways. So if B has occurred, that excludes A from occurring. Let me give you an example. Suppose that our experiment consists of picking a single card out of a standard pack of cards. And let's suppose that A is the event that we get a king, and B is the event that we get a 6. Now, are they mutually exclusive? Well, let's think about it. If we know that the card that we've picked out is a king, in other words, that A has occurred, can B occur at the same time? At the same time as getting a king, can the card that we've picked out be a 6? And clearly that's not possible. If it's a king, it's definitely not a 6. So getting a king excludes it from being a 6, and vice versa as well. So another example, suppose that we pick a single card out of a pack of cards, and A is the event that we get a king, and B is the event that we get a diamond. Are they mutually exclusive? And the answer is no. The fact that we've gotten a king does not exclude the card from being a diamond. It could be a diamond at the same time. So in that case, A and B, being a king and being a diamond, are not mutually exclusive. And that leads us now to a very, very important set of rules in probability, what are known as the addition rules. Now, the addition rules there's two of them. The first one is the addition rule for mutually exclusive events. So, for mutually exclusive A and B, the formula that we have here is that the probability of A or B, which means A union B, is just the probability of A plus the probability of B. Just add the two probabilities together, which is very nice and very simple. Unfortunately, that particular formula will not work if the events A and B are not mutually exclusive. So we can just say for general events. And this other version here is called the general addition rule. But for general events A and B, so the, if you like, extended version of that is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. The probability of A and B. Right, so if we're asked to work out the probability of one thing or another, we're going to have to use one or other of these two formulae here. And the one that we have to use will depend on whether the events are mutually exclusive or not. Let's go and have a look at a question on this. On the question sheet here, question 2. Now, in this question here it says, in a group, 6 of 10 men wear glasses and 5 of 12 women wear glasses. If 2 people are chosen at random from the group, what is the probability that they are either both men or both wear glasses? And I have to say, the one word that jumps out at me immediately on reading that question is that small little word on the last line, the word or there. Both men or both wear glasses. So that's going to mean I'm going to use one of these two formulae here. Look, let's just kind of summarize the data that we've been given at the beginning here. First of all, we're being told about men and women. So we're just going to present this in the form of a table. So men and women. And we're being told that some of them wear glasses and some of them don't. So I'm just going to say no glasses. So some wear glasses and some don't. Now what does the question say? It says 6 of 10 men wear glasses, which means that 4 don't, out of a total of 10. And then for the women it says 5 of 12 women wear glasses, which means 7 don't, out of a total of 12. Now, how many in total then wear glasses? The answer is 11. 6 plus 5. And also 11 is a number that don't wear as well. Now, whether you add these up going down, men and women, or you add up those who wear glasses and those who don't, the total number of people in the group that they're talking about is 22. So now, that little table summarizes all the information that we've been given and makes it readily accessible. So, okay, what's the experiment here? The experiment here is that all 22 of the names go into a hat. And as the question says, 2 of the people are picked at random. So writing this down in probability language, it's going to be choose 2 from the entire group. And the entire group is 22. Now, because each pair of people in the group are equally likely to be chosen, we can use the R over N formula. So N is equal to then, let me just write it down first, it's 22, choose 2. And 22, choose 2 on the calculator here. Yep. On the calculator, 22, choose 2 is equal to 231. Grand. Now, in a situation like this one here, my inclination is first of all to call the first thing that they talk about A, the second thing they talk about B, and because whichever of the 2 formulae that we're going to use here at the end of the day, we still need to work out the probability of A and the probability of B. Let's do each one of them individually. So let's suppose that we refer to A, the event A, as being what they say here first, both men. Absolutely. So we understand the concept, I'm sure, that when somebody puts their hand into the hat with all the names in them and picks out 2 names and reads the names out, that they're both men. But we need to write that down in probability language. So we can say, choose 2 from the total number of men in the group. And looking at the table there, the total number of men in the group is 10. So we choose 2 from 10. So the OR value for that would be 10, choose 2, which we just work out. Now, here we go. So 10, choose 2 is 45. And therefore, the probability of A, in other words, the 2 people picked out are both men, the probability of that is going to be 45 over 231. And we can let the calculator simplify that fraction. 45 over 231, and that's 15 over 77. Good. Now, let's work out the probability of B. So the second thing that they talk about here is that the people that are picked out, they both wear glasses. So B is that they both wear glasses. Right, so again, let's express that in probability language. How many people in the group wear glasses? The answer is 11. So we need to choose 2 from the 11 people who wear glasses. So choose 2 from 11. Now, this time around, the OR value will be 11, choose 2, which we can just work out here. So 11, choose 2 is 55. And therefore, we can say the probability of B is going to be 55 over 231. And what is that going to come to? Well, let's just put it into the calculator and simplify it. 231. That comes to 5 over 21, actually, for that. Now, the dilemma at this stage is, do we use the simpler formula for calculating the probability of A or B? Just add the probability of A and the probability of B. Or do we have to use the more involved so-called general addition rule? Well, I have to say my attitude is that I always assume the worst. So I'm going to say, look, let's take it that the events are not mutually exclusive. And let's take a look at A and B. In other words, that both events occur. And if, when we consider this, we say, do you know what? That can't happen. And if that can't happen, well, then it means that the events are mutually exclusive, and we just go back and use the easier formula. Well, let's see what the story is here. A and B. What does A and B together actually mean? I'll do it up here. So A and B. That means that the two names that are picked out of the hat are both men, that's A, and they both wear glasses, that's B. Now, is that possible? Is it possible to pick out two names from the hat, and when we read out the names, we realize that they are both men and they both wear glasses? And the answer is yes, that is possible. So therefore, these events are not mutually exclusive, and we have to use the more general addition rule. So yeah, it is possible. There are 6 men here who wear glasses, and we could quite easily pick out 2 of those 6. So we can just write this down in probability language. We can say it's choose. From this here, we can say choose 2 from the 6 men. We'll say men with glasses. So the OR value for that event there would be 6 choose 2. And 6 choose 2, okay, for that would be, sorry, we just put it over here. It's going to be 6 choose 2 is equal to 15. So therefore, from that we can say the probability of A and B is going to be 15 over 231. The end value there was 231. So we just simplify that fraction. So it's 15 over 231, and that's 5 over 77. So now we can write down the general addition rule, as it's called, the probability of A or B, in other words, that we get both men or both wear glasses, is the probability of A plus the probability of B minus the probability of A and B. And we've got all these numbers, so we can just fill them in. From what we got back over there, the probability of A is 15 over 77. Plus the probability of B is 5 over 21. Minus the probability of A and B we've just found to be 5 over 77. So we just get our calculator and we work that out. We add up those 3 fractions. So we'll just do that now. So we can just say 15 over 77 plus fraction 5 over 21, and then minus fraction 5 over 77. And that comes to 85 over 231. So 85 over 231. And there's the end of that question there, which is built on the idea of the addition rules. So that's grand. Now we need to move on. The next thing we're going to have a look at after that is what we call conditional probability. Now, just let me explain first of all the idea of conditional probability. Okay, suppose we have a standard pack of playing cards, 52 cards, and what I'm going to do is I'm going to shuffle those 52 cards, and then I'm going to fan them out, and I'm going to ask somebody to pick out a card at random from that pack of cards. And I want to find the probability that the card that the person picks out is a king. Well, as a simple question, the answer is obvious. There are 52 cards in a standard pack of cards, of which 4 are kings. So therefore, using the OR over N formula, the probability of that card being a king is 4 over 52. That's fine. But let's take it back a step for a minute. Imagine that we are conducting that experiment. So I shuffle the cards, I fan them out, and I offer them to somebody. And somebody else then picks a card at random from that pack of cards. But imagine that as they do so, their hand slips. And even though I cannot see what card they picked out, I do get a glimpse of colour, so that I know that the card is a picture card. In other words, it's either a jack or a queen or a king. The question here is, does that bit of extra information, does that alter the probability of getting a king? And the answer is yes, it does. Common sense tells me that if we know that the card is a picture card, the probability of getting a king is no longer 4 out of 52. It's 4 out of 12, because there are only 12 picture cards in a pack of cards. Now, that's called conditional probability, and we could write it down here as the probability of getting a king. And the way this is written down is a vertical line straight down like that. Given that is the way we read that out. Given that the card is a picture card. So given that additional knowledge there, right, what's the probability that then the card is a king? And that's called conditional probability. Now, in general, we're talking about knowing that an event A has happened, finding out the probability of another event B. And that can be written down as the probability of B given A, like that. So the second event that's written, the one that's written after the straight line, is what we know has happened. And we're trying to find the probability of the first event mentioned. Now, there is a formula for this, which I'm afraid you're going to have to learn because it's not in the maths tables. And it goes like this. The probability of A and B on the top line of a fraction divided by the probability of what we know has happened, which is A. So the probability of A. And that's the formula for conditional probability here. Very good. Now, let's go and have a look at a question on this here from the question sheet. And this is question 3 on the question sheet. Now, it says here in this question, a student takes 2 tests, A and B. The probability of passing in test A is a half, and the probability of passing in test B is 3/4. The probability of passing in both tests is 1/3. Now, the question says, if the student passes in test A, what is the probability that she also passes in test B? Now, one of the problems that people have with conditional probability is recognizing the need to use it. How do we know this is a conditional probability question? Well, the usual way of being able to identify that is you realize that they're asking you for the probability of something, but they're telling you something that they didn't have to. So they're asking us for the probability that this student passes in test B, but they're telling us that she's passed in test A. They didn't have to tell us that. So I'm just going to write this down. They're looking for the probability that she passes test B, given that she has passed already. So she passes test A. Now, luckily for us, this is very convenient because I always tend to call what I know has happened A. So A is that she passes test A, and I call what we want to find the probability of B. So that's what we're going to talk about there. Right, okay, so we're going to use this formula up here now in a second. Now, to be able to use that formula, we need to know the value of the top line and the value of the bottom line there. Do we know that? Do we know what we call here the probability of A, which, if you like here, is the probability that she passes test A? And if you look back at the information given in the question, I think we do. It says here, the probability of passing in test A is a half. So that's going to be a half. Now, we don't actually need, funny enough, we don't need the probability of B. We don't need that. We just need the probability of A and B. And in plain language here, the probability of A and B is the probability that she passes both tests. She passes test A and she passes test B. So she passes both tests. Now, do we know that from the question? And I think the answer is yes again. It says the probability of passing in both tests is a third. So now, that's great because we can finish up now very quickly because we know the top line and we know the bottom line from the formula, and we can just say, thus, the probability that she passes in test B, given that she passed in test A, is going to be the probability of A and B which is 1/3, divided by the probability that she passes in test A, which is 1/2. So now if you work it out on a calculator, or as you know, when you've got one fraction over another, if you take the fraction on the bottom line and invert and multiply by it, you get 1/3 multiplied by 2/1. So the answer for that then is 2/3. So that's an example of conditional probability. Fine, okay, now we just had a quick look at that. The next thing we want to have a look at after that is the idea of independent events. Now, independent events, from the point of view of students, these are very, very often confused with mutually exclusive events. They're completely separate. Mutually exclusive means that they cannot happen at the same time. So if one of the two events happens, it excludes the other one happening. Independent is completely separate, completely different. And we can just say here, two events, A and B, are independent. In plain, simple, casual language, if they do not affect each other. They do not affect each other. And what that means is, i.e., right, the probability of B is not affected by whether or not A has occurred. Now, I'll give you an example. Suppose we get a coin and we toss the coin again and again. And let's suppose that A is the event that we get ahead on the first toss, and B is the event that we get ahead on the second toss. The probability of getting ahead on the second toss is 1/2, and it's not in any way influenced by whether or not we got ahead on the first toss. So those two events there are independent. Now, the definition of two events being independent, the mathematical definition, so we can say A and B are independent They are independent if the probability of A and B is equal to the probability of A multiplied by the probability of B. And that's called the multiplication rule. For independent events. Grand, so now can we go to the sheet again? Can we have a look at a question on this? It's question 4 here on the sheet. And this comes from the Leaving Cert in 2013. And the interesting part of that is the A part there actually. They ask you to explain each of the following terms, which we now should be able to do. The sample space, first of all, as I mentioned earlier, that's the set of all possible outcomes when the experiment is performed. And then they ask you to explain mutually exclusive and independent. And that really is, checking to see, can students distinguish between the two? Mutually exclusive, which means that the two events cannot happen at the same time. If one of the events happens, it excludes the other one from happening. And then independent, as we've just seen here, that they have no effect on each other. And they are completely separate ideas. And you must be able to keep them separate. So now, I'm not going to write those down. We're going to have a look, though, at the B part here of the question. So it says, in a class of 30 students, 20 study physics, 6 study biology, and 4 study both physics and biology. And the question says, in part 1, represent this information on the Venn diagram. So fair enough. Here's the Venn diagram. I'm just going to make a copy of it here. So here we have the way they've got it drawn like that. and then the other one is there. And I'm just going to call P here for physics and B for biology. Now, in a class of 30 students, so the number of students then in the entire sample space, okay, we can say the cardinal number then of the sample space is 30. And the information that they've given us here, the cardinal number of physics, according to the question, is 20, and the cardinal number of biology, according to the question, is 6. And they tell us that the number that study both, which would be physics intersection biology, is 4. Well, look, we can start from there. First of all, if 4 study both, well then the number in here is going to be 4. And if there's 4 in there, how many study physics alone? Well, because the total number that study physics is 20, subtract 4 from 20, and the number in here is 16. And then the number that study biology, well, if 4 study both, but only a total of 6 study biology, there can only be 2 in here. So 2 in there. And if we add up those, we can find out then how many study neither physics nor biology. Well, 16 and 4 is 20, plus 2 is 22, out of a total of 30, so that has to be 8. Just take 22 away from 30, and you get 8. Now, so that's part 1. Now, we're heading into part 2. It says, a student is selected at random from this class. The events E and F are, E is the event that the student studies physics, and F is the event that the student studies biology. And it says here, by calculating probabilities, investigate if the events E and F are independent. Fair enough. So E is the event that the student studies physics. Okay, so what is the probability then that a student picked at random studies physics here? Well, out of a total, I'm just going to say here, by the way, the overall N value is 30 because there are 30 students in the class. But for the fact that a student picked at random studies physics, how many students study physics? And the answer is 20. So OR is equal to 20. And therefore, the probability of the event E, in other words, that a randomly selected student studies physics, is going to be 20 over 30, which, if we simplify down, is just going to be 2 over 3. So that's the event that the student studies physics. Just go on to the next page here. And after that, the event F, according to the question here, is that the student studies biology. So studies biology. Now, same value of N, because there are still 20 students in the class. So what's the probability of F that a randomly selected student studies biology? Well, according to the question there are 6 biology students in the class. So the probability of that is 6 over 30, which is 1 over 5. Now, if we're going to check that definition there, we're going to have to check and see if the probability of E and F is equal to the probability of E by the probability of F. So therefore, we now need to talk about the event E and F. Now, what does E and F mean? It means that the student that is selected studies both physics and biology. Okay, if we have a look at that, what's the probability that a student chosen at random studies both? Well, from the Venn diagram, that's going to be 4. So the probability of E and F then is going to be 4 out of 30. So 4 out of 30, if you divide above and below by 2, you get 2 out of 15. So now, what we need to check to see if they are independent, just to highlight what we're doing here, right, what we are doing. Are they independent? Query, okay, are they independent? And basically the query is the probability of E and F, this is a question mark, alright, the probability of E and F, is that equal to question mark, we don't know yet, is that equal to the probability of E multiplied by the probability of F? Right, well, we have all the numbers that we need. We just have to check. The probability of E and F we've just worked out to be 2 over 15. The probability of E was 2 over 3, and the probability of F was 1 over 5. So what do we get when we multiply those two fractions? Well, hang on. 2 over 3 by 1 over 5, multiplied top by top, you get 2 by 1 is 2, and then bottom by bottom, and that is 15. So actually, the answer is yes, they are equal. Okay, when you work out the two sides, they are exactly the same. So in this case, we can say yes, the events E and F are indeed independent. Now, I have to admit that when I first saw that question in the exam, before I got around to checking it out, I kind of assumed that the answer was no, because most of the time in a situation like that, the answer will be no. But this is one of the rare cases where the answer is actually yes, that they are independent. So what does that mean in that scenario there? It means that, for example, if we pick a student out at random and we know that the student studies physics, for example, that does not in any way influence the probability that the student also studies biology. Okay, it doesn't have any effect on it, it doesn't change anything, and vice versa. So that's a summary of some of the key ideas in probability, and I'm afraid that's all that we have time for today. So we'll go on with this tomorrow, and tomorrow we'll be looking at statistics. Goodbye. See you.